So we want to talk about unit conversions and the use of microscopes. But I want to call the note Microscope Numeracy. Start out talking about unit conversions. Okay. Really simple unit conversions, ones that I really hope that people are familiar with before they even walk in the door today. Like for example, 1 kilometer equals blank meters. Can anybody feed me that answer? 1,000. Beautiful. What about this? Make it a little harder. 1 centimeter is equal to blank millimeters. 10. There we go. How about this one? I'll throw a curveball at you. 6.75 meters is equal to blank centimeters. Can you handle that? Yeah, 675. Beauty. All right, so that was the easy stuff. So I'll put a happy face beside it because it makes me feel happy that I know that stuff. However, do you think that a kilometer conversion is useful for microscopes? No. Maybe telescopes. I don't know what other kind of scope, but not a microscope, okay? So let's be stethoscope. Oh, good Lord. Let's not even talk about horoscopes. Here, let's try this. 1 micrometer is equal to, and I'm going to give you this one for free. 1 micrometer is equal to 1. Now, if I told you a micrometer is equal to 1/1000th of a millimeter, what fraction of a meter would it be? Can you do that? 1/1000th of a millimeter is a micrometer. What would its fraction of a meter be? Yeah. A millionth, yeah. So I'm going to write it as a fraction. Sorry if you said it, I didn't hear it. 1/100000th of a meter. That's the definition of a micrometer. But I also want to pay some attention to this letter here, this sort of curvy M. It's not an M, and it's not a U. It's the Greek letter mu. Isn't that cute? So it's not an M and it's not a U, it's a mu. It's because we already used lowercase m for milli and uppercase M for mega. So we had to have another letter for micro. So we just kind of stole from somebody else's alphabet. Okay, so that's all right. It's a mu and it indicates micro. And that's a pretty, it's universally accepted letter for the prefix micro. Okay, so if you've never seen micro as a prefix before, that's how we represent it.
So it's just squiggly.
It's not just a squiggle. It looks like this. I'll draw it big for you. Big old curly MU hybrid, okay? Okay, but it's all saggy in the middle and curvy on the sides. And it's micro, okay? So micrometer. All right, so let's try one that has micrometers. 50,000 micrometers is equal to how many? This is easy. Millimeters. 50,000 micrometers is how many millimeters? Yes, sir.
5,000.
No. 50. Yeah, 50. There are 1,000 micrometers in 1 millimeter. So 50,000 micrometers is 50 millimeters. So let's try this. 4,762. Try that. Give you another shot at it. Micrometers is equal to how many millimeters? Yes, sir.
4.762.
Yeah, 4.762 millimeters. And actually, that's useful. We've gotten away from the idea of kilometers and meters. You're never going to have like a field of view. That's what you call that sort of circle that you're looking at when you're looking through the microscope. You will never have a field of view that's 1 meter wide. You will never have a field of view under a microscope that's a kilometer across, okay? But millimeters and micrometers, I believe that. That's something that I could look at under a microscope. That could be a reasonable scale, okay? So that's why we're focusing on it. What about this? Little numbers. 23 micrometers expressed as millimeters. And people can multiply by 1,000, but can you divide by 1,000? Yes, sir.
0.023.
Beauty. 0.023 millimeters. Now, if you're somebody that thinks about decimal places and moving decimal places when you divide by 1,000, what we've really done here is dividing by 1,000, you move the decimal place over once, twice, 3 times, boom, 0.023. Okay, if that's the way you learned it in elementary school, then that's okay. You can still think that way. But really, we're dividing by thousands, okay? How many people learned that way in elementary school? Yeah, a sizable portion of the room. That's pretty common. There are other things other than micrometers and millimeters. Like, for example, we could talk about units of angstroms, 10 to the power of negative 10 meters. But we're not going to discuss that in this course. If we're talking about this in terms of millionths and billionths, what would this one be? It's not a seventh. Pardon me? It's a lot, yeah. It would be, no. It would be 1/10,000th of a micrometers. Yeah, so this would be 1/10 billionth of a meter. That's really small. The only reason we really might think about it is because it's kind of roughly the diameter of a hydrogen atom. So that it might be useful to us. It's maybe a little bit of an old-fashioned term, but it has some sort of a scale relevance. Okay, let's try something else. We want to keep on moving with our idea of microscope numeracy. Let's talk about magnification. This is part B of the note, if you want to label your notes this way. Magnification, a new part to the note. Now everybody knows that when you look through a microscope, there are multiple lenses. And if you didn't know that, and you didn't catch that in grade 9 science, then maybe you just weren't paying attention. That's okay. I am going to plug in my computer here because apparently it's decided that its battery has run out. Just give me a moment before my computer goes to sleep. All right, back at it then. I'm plugged in. So there's two lenses that you want to think about in particular. Ocular. I don't want to say names, but you, be quiet. Ocular. There's the objective lens. And together, they give you total magnification. I'll just say total mag, okay? So the objective lens, OBGECTIV, objective lens.
What's the first one?
Ocular.
It looks like
OCULAR. Now, I'm going to make this available to folks in a little bit. But let's talk about what those parts actually are. So my video is a little bit fuzzy, but this part here is the ocular lens. And these parts down here are called the objective lenses. And the objective lenses are those lenses that you can spin at the tip of the microscope. And those people from grade 9 science that remember this part's called the rotating nose piece. And you can turn, it kind of looks like a nose, right? And it's able to rotate. So you can rotate between the magnifications by switching your objective lens. Now, if you want to know why they're called what they're called, ocular has the same root word as the Latin word for eye. So it's the part that you put your eye up against, okay? The objective lens, really, the object that you speak about in English is the thing that you're really focusing on in an English subject. So when we're talking about the objective, what's the object that you're looking at? Well, that's the part that points at the object that you're looking at, your objective lens, okay? So the words make a lot of sense. The only one that we can find in this diagram that actually has a Latin sort of base to it, and I know people are getting tired of using Latin words as the basis for communication. That's fine. Ocular is the only one that has that Latin, and a lot of people don't even call it the ocular lens, they'll call it the eyepiece. So if you call it the eyepiece, that's fine too. So let's pull this thing away. Let's say that we have a magnification at the ocular of 10 times. That's a really common magnification for an ocular lens. And another really common magnification for an objective lens would be 40 times. What would be the total magnification then? Anybody want to tell me? Spencer?
400.
Yeah, 400. You multiply them together. Thank you. You said 400.
I said 400.
Yeah, you did say 400, and then I said 40, sorry. Yeah, 400. What if you have an ocular? Now, this is less common in the microscopes that we have. Most of our microscopes have a 10 times ocular piece, but you might still find some 15 times ocular pieces in our collection of microscopes. But if we had a 15 times ocular piece and the total magnification was found to be 150 times, what would the objective lens be that we were looking through? Yes, sir? 10, yeah. This is like a nice linear equation, right? Well, it's like a y equals mx equation. It's not even a y equals mx plus b. All right, what about this one? What if I know that my objective lens is 25 times and my total magnification is 125? What would my ocular lens have to be? Yes? 5, yeah, 5 times. Now we don't have any of those in our collection, but it's possible that that would be an ocular lens magnification. Now that's not too tricky, because really, if I'm looking at the ocular lens and the objective lens, you can look at the diagram here. It's hard to see on this diagram, but there actually are magnifications like 10 and 25 scratched or printed right into the side of those lenses. Okay, so you can see those numbers. You don't have to look anywhere for them except right on the piece of equipment itself. Okay, so that's something you would want to record while you're making observations. And we'll talk about making microscope observations on another day, but we're going to start into the basics right now. I want to talk about field of view.
Is this a new one, or is this?
Yeah, this is the next part. So if you want to call this part C, if you're organizing yourself in that way, this could be part C. Field of view. And a lot of people short form field of view as FOV, field of view. Okay? Now, if I talk about field of view, what I mean is, it's a new part, yeah. What I mean when I say field of view is that circle that I see when I look through the microscope. And I know that everybody here has used a microscope. If you had grade 9 at this school, you look through the microscope and you see this circle, this field where all the stuff could be that you're looking at. That's called the field of view. And it's got a diameter, because it is circular. If you didn't use microscopes last year, don't worry. I'm going to give you the training on it. It's not a big deal. It's not a huge hole in your knowledge. It does have a diameter. For our purposes, we've gone around, we've looked at our microscopes, and I'm going to tell you right now, for high magnification, the field of view has a diameter of 400 micrometers. Of course, we have a medium magnification, and we have a low magnification. Now, I got to ask you, as you go down from high magnification to low magnification, should the actual field of view, should it be getting bigger or smaller? Yeah. You're zooming out, remember? Bigger, yeah. Because that's what magnification getting lower means. Lower magnification means it's like you're zooming out, because that's the language we've all kind of come to understand when we're looking at Google Maps or something like that. So we're getting a wider field of view. So 1,600 micrometers. You know, Google Maps does make me think of this. You zoom in, you get a higher magnification. You zoom out, you get a lower magnification. And 4,000 micrometers for low magnification. That's for our microscopes. Now, that's going to vary depending on what the ocular is and what the objective is. But for our microscopes, this is roughly what the fields of view are, okay? Now, I'm going to refer to them in plural as FOVs, even though I know grammatically it should be fields of view. I'm going to say FOVs, which would be field of views, which is silly. But anyway, let's say that we looked at this on low magnification, and I put a ruler underneath of my microscope. That's totally plausible. You could put down a ruler instead of a slide. And so the pink here is going to be the ruler. Okay. And I could see, after laying down my ruler, can you see how many millimeters are present there? 4 millimeters across. Let's say that I actually put my ruler down on low magnification and I got there to be 4 millimeters across. Does that agree with what we just said over here?
Yes.
Is that right?
No.
It's the math we did earlier, right?
Yes.
Does 4 millimeters equal 4,000 micrometers?
Yes.
Yes, sir, it does. And that's what you would find if you took a ruler and you put it underneath the microscope. Now, you'd have to have a translucent or transparent ruler. Don't do it with an opaque ruler. It really doesn't work very well. But a transparent or translucent ruler works best. And our low magnification, that's what you're going to find with our microscopes. You get 4 nice millimeter demarcations there. That's a nice way to just sort of prove that, I'm not lying to you, okay? But it could be a way to calibrate our magnification values and check on what our fields of view are. All right, let me take that guy away. I want to talk about Approximating size.
Another note.
Yep.
Is this like a different note or just a different topic on the
Just a different topic on the same note.
Oh, right.
So finding approximate size is going to need you to take a look at your field of view. And let's say that we look at this again on low magnification, which means we have 4,000 micrometers for our field of view diameter. Okay? And let's say that as we're looking under our microscope, we see a ant's head. This is an ant's head. See the little pinchers there? Okay. And I'd like to know, I don't know if this ant's head is attached to the rest of the ant or not. It's really not my business right now. I don't want to get too involved. But I want to know how big this ant's head is. Okay. And I look at this field of view and I say, I could use an approximation method to figure that out. Anybody give me the message or the method that I would use to do that? How can I figure it out? Yeah?
How many ants' heads can you fit across the diameter?
Yeah, I think that seems reasonable. We could sort of eyeball it and say how many ants' heads can fit across this diameter. As I'm eyeballing it, looks kind of like, can you guys see that it's about a third? That was my intent when I did this, just sort of for the idea of it. So I could say, hey, look, 1/3 of the FOV equals 1 head. Okay? And so if I want to calculate size of head, 1/3 times 4,000 micrometers. What's a third of 4,000? Yeah?
It's about 1,333.
Beauty. And 3 repeated, right? Forever and ever. But we'll stop at the whole number, micrometers. Or you could say it's 1.333. What unit would that be? Millimeters, yeah. Okay? About. And if we went back to our reference sheet that I gave you just a few minutes ago, a reference of the magnifications, we did say that this was low magnification. So let's just say that it was a 400 times magnification. And we're going to go through the layout of how you should record all this information in another lesson, but this is all the information you might want to think about, okay? So low magnification might be 400 times magnification. And you might also want to make some qualitative observations. And again, we'll talk about the layout of those kinds of observations later on. You might say the ant's head appeared to be approximately 1/3 of the, sorry.
No, I'm fine.
Oh, somebody else's ant's head, okay. Of the FOV diameter. And we might make some other qualitative observations, but for our purposes right now, that's all I really want to focus on. But we should have all those things. The magnification's field of view, the actual magnification, any calculations that are required, and any qualitative observations that we might make. And again, we'll go into the details of how I'd like that laid out at another time. I think that's pretty much all I want to take a look at for now in terms of the numbers. So that's a few different ways to look at the numbers for microscope numeracy. What we've talked about, let's just make sure that we've got it. We've talked about magnification calculations. We've talked about different fields of view for the diameter of the field of view. Talking about making observations and figuring out how big stuff is based on the size of the field of view. And we've talked about, where did I leave it? Reasonable unit conversions once we know how big that thing is so that we can, figure out what that scale really means. I'm going to pause it there.